Hello and welcome to chapter number 7, and today we want to talk about satellite testing. So what are the objectives of satellite testing? Well, the objectives are to perform a systems verification, to qualify your principal parameters, to verify your global concept, and also to approve your compatibility with reference standards, reference missions, reference cases. Lastly, the methodology and your logic integration is part of the objectives of your satellite spacecraft testing. The important items are usually the electrical architecture you want to test on. You want to determine operational margins due to an EMC test, temperatures, etc. You want to acquire and test the functions of your spacecraft, as in the previous section, the TMTC, your radio link you want to test, and you provide and want to verify the functionality of the system. You also want to check on the performance of all your systems. So when you have a camera system, you want to make sure that it's actually giving you the quality of the images and research data you need for your mission. And you have several material and structures you want to test on, especially vibration and thermal tests on those materials. The critical testing involves the radioelectric testing for the RF tests with the installed structure, but also the RF axis. So for instance, is the satellite transmitting in the right direction where you're expecting it to be? But it also comprises the antenna compatibilities. Yeah? So if you have two ground stations, are they able to recognize each other, and are they able to determine the signals being transmitted between the 2 points? You have electromagnetic testing, especially the EMC tests. You have equipment tests. Those are independent tests for all the different equipment you have, especially noise tests for your cabling. You want to, for instance, make sure that you don't have any interference coming from external sources into your equipment. And the satellite itself, of course, you want to check the complete onboard equipment, that everything is well tested before you put it up into space where it's out of your reach. And you want to test across different component layers. So you don't want to only test the satellite as a whole unit. The tests start much earlier on lower levels, like on unit or on assembly level. And besides the electrical tests, there are mechanical tests. So we have vibration tests, we have structure tests. So you want to check how is your system reacting to vibrations that might occur or will occur for sure during the launch of the satellite. Is your structure able to support everything? Yeah? Imagine you have long booms or any structures that are deployed. Is that all tested well and it stays where it should be? You have acoustic tests because it is very loud during the rocket launch, also inside of the payload bay of your satellite bay. So you want to make sure that all those really loud noises don't damage the satellite. That's why you do acoustic testing. You have shock tests, for instance, at launch separation. So even when you reach space already, the satellite needs to be deployed in the orbit. And this is sometimes done by an explosive charge and is usually coming with shocks, either directly from your launch separation, but also when other satellites on a rideshare mission are deployed. And lastly, you have physical checks, for instance, on your gyros, on your mass, on your fuel. So you want to check that everything is within the margin where you want to have it. And center of gravity is a very important point to determine. So you want to know where is the center of gravity of your satellite, because this is later really important for your attitude control system. Let's look into the thermal testing and how we can have a subdivision of the thermal testing. So the thermal tests usually come in 4 different categories. You have the thermal cycle test, you have a thermal vacuum test, a thermal balance test, and a special test. So the special test is the easiest to handle here because this is just a specific test for this specific unit. So it's really hard to tell what is a general special test, but it really depends on what type of unit you have. Imagine you have a specific infrared cooler for your infrared camera. Then you, of course, want to determine that the thermal system also is stable for this cooler unit. This is a special test you do besides all the other tests. Thermal cycle is to provide for the changes between eclipse and non-eclipse, so solar phase. So you have temperature changes, and you're gonna have on a LEO mission a lot of temperature cycles you go through, and that's why you're gonna cycle your units and your satellite a couple of cycles between minimum and maximum temperature to make sure that everything stays within the limits. You have a thermal vacuum test. So of course, in space we don't have we only have conduction and we only have heat radiation. So since there's no convection, no air that is helping us as on Earth to get rid of excess heat, we can only conduct within the satellite, and then we have to radiate it into space. And to simulate these conditions on Earth, we need the thermal vacuum test to remove all the oxygen or our medium that is used for the convection and only rely on radiation for the thermal vacuum test. And lastly, we have the thermal balance test where you check under vacuum conditions, and we also see that here, vacuum or under ambient pressure, how the temperature is balancing within the satellite, within the certain units. Are you having hot spots? Are you having cold spots? And how do you balance the overall temperature? Because usually you would like to avoid great gradients within the satellite. So big temperature difference because it's the stress of your structure. So on component and subsystem level, you would usually have thermocycle and thermal vacuum test. Rather seldom you would have a thermal balance test, maybe on subsystem level, but usually a thermal balance is among the units, so between the units, not within one component unit. But for the system, so this is the satellite itself, you would usually only have thermal vacuum and a thermal balance. So after you cycle all the components, you don't have to cycle the whole satellite again because you have already shown that all the different components and subsystems survive the thermal cycles. So you only go for thermal vacuum, thermal balance, and special tests. And then we have the different test techniques. So we have the qualification test and the acceptance test as different categories. So you want to qualify your model, for instance, but you also want to accept, you have the acceptance test that everything stays really within the limits. And this is also important for any reviews you might have with your satellite mission, with your stakeholders and so on. And well, we talked about the test restraints, and as for the test equipment, for the thermocycle and thermal vacuum, you need heaters and eventually a deep space simulator because you need to simulate space conditions and you need to simulate cold space. So even if you radiate heat out of your system, you need to be able to remove this radiated heat out of your test environment, as it would be in space. And as for the thermal balance, you also have now the influence of external heat sources like the sun. Yeah, the sun is causing additional heat to be heat intake into your satellite, and you want to simulate this with thermal balance because this is an important influence on your whole system and how your thermal control system is balanced. You can also use an infrared test chamber or a space simulator for this. And here we see an example of a big space simulator with a satellite in there. We have some lamps to simulate sunlight and a big mirror to reflect that. And this whole chamber can be under vacuum conditions. Or a different model here, instead of having a big solar lamps, we use xenon solar simulator and also put it into a vacuum chamber. So we could use a cold blank space simulator, which are quite cheap for the test of single components. And it's very fast and easy to manage at that point. However, you can only you can only have homogeneous heat fluxes, or the ambient temperature is adjustable at this point. As for a solar simulator, you produce a high quality and realistic solar and vector environment, but it comes at very high cost on the other hand side. Another category are the infrared simulators by the use of quartz lamps, and with this you can simulate the highly dissipating heat loads into the system, but the radiation again is not homogeneous because you have many separate lamps, and the spectrum really depends on the lamp power you use there. So imagine you want to have the infrared energy from the sun, you want to simulate that. It's a very high density of energy there. So it's not so easy to have a homogeneous field there. Lastly, you can have the infrared simulator with the surface of patch heaters. So this is used to simulate a three-dimensional environment and a temperature-dependent heat load. Yeah? By using those patch heaters, you can introduce additional heat into the system, and you have the infrared simulator to have the external environment. This is a very complex test setup, and it needs a very precise test preparation in order to be successful there. As for the testing procedures, for the thermal test, we usually go for the vacuum environment. So we want to have extreme orbit temperatures to be simulated first. And we want to have the vacuum radiation. So this is to verify the thermal model. So usually you already have a model. You model the thermal system of your satellite and thermal behavior, and those tests are used to determine their behavior and to verify that your model is actually in sync with your reality, with its certain findings. And to perform those vacuum tests, those thermal tests, you can use particular test facilities. Yeah? I mean, aside from the thermal test chambers we just saw, you can have electrical chambers, so an anechoic chamber for the radio frequency testing. Antennas could be tested in a compact test range to simulate far field conditions. We have mechanical test facilities for the vibration simulation, and on an electrodynamic table, and vertical, it's been a shaker, so-called, and of course the thermal simulation and the thermal test in a thermal vacuum chamber, thermal compartments, and so on. What are the important functions we want to test? Well, basically, in terms of the system, we want to test anything. We want to test our sensors. We have a great variety of sensors across our satellite. We want to test all of them. We want to test our inertial reference sensor. If we have an Earth sensor, star trackers, so star cameras, we want to test all those functions that are related to our attitude control and attitude determination system, that they work and that we actually have a good solution for our attitude later. We also want to test our actuators. So if we have reaction or momentum wheels, we need to test those, that they're working properly. But also thrusters need to be tested somehow. If we have instruments on board, of course, I mean, this is usually the reason why we launched our satellite. We want to test that all of our instruments actually work. So if we have a telescope, antenna, or radar on board, we want to test those units, doing specific and special tests to make sure and verify the functionality of this system. An onboard computer as the main unit inside of our system, of course, needs to be tested very well and be well understood in case of there are any discrepancies or any failures and issues on board, so you can identify and resolve the failures later on, just in case. Well, I would like to give you an example how this whole testing is done on a real project. Since in theory this whole testing is a little bit too abstract maybe, and with some examples the Flying Laptop is quite good to give you a feeling of what is involved in a small satellite project and in terms of testing. The first point is the product safety we should talk about. I mean, yes, Flying Laptop is an academic satellite, so there's no customer involved. If you have a commercial satellite project, of course, there's some customer and maybe even some government agencies involved. that they want to have a proof of a certain product safety. But the basics for flying laptop, even if it is just an academic satellite, is that the whole system is radiation hard, and the satellite bus, is one failure tolerant. So a single failure can happen without having an effect on the whole system or the main functionality of the system. Also, no harmful substances or explosives can be used. And the code of conduct of space debris mitigation and the is followed, and as well as the frequency coordination with the ITU. For the space debris mitigation, the code of conduct, we see here a graph. So it basically requires your satellite to re-entry after 25 years of your mission, your elapsed mission, to avoid space junk or space debris. And there was done some simulations. So this is the graph for a 600 kilometers orbit without the orbit mechanism and with an e-orbit mechanism. So you can see that it takes much less time to re-entry the Earth atmosphere if you have a de-orbit mechanism like this one, which is basically a big sail that increases the drag of the residual atmosphere with the residual atmosphere. And the last point for the product safety is training and reviews with experts from industry to ensure that all the mission is on track if you don't have this knowledge in-house. For all those testings, you need infrastructure. Yeah, we talked about the thermal test. You need a thermal vacuum chamber. The integration to really assure your cleanliness should be done in a clean room, in a clean environment. So all the integration, especially of the optics, are done in the clean room. We have a ground station for the compatibility tests and the operations tests. And of course, for all the environmental tests, they need to be done in different environmental simulators. The first test is the system simulation of flying laptop. So in order to do the system simulation, so how will the satellite behave in general as a unit, we use a hybrid testbed with a software model of flying laptop. So we have the simulator in different inputs and outputs and a kernel, and then you have equipment models. So you have models of your equipment in your spacecraft simulator, and all those models are connected to the actual onboard computer. The actual onboard computer or engineer model of the onboard computer, which is then connected to your telemetry, telecommand front end, and your power and your control PC. And the simulator is used to simulate the space environment. We simulate all the components as a model in the space environment, but we use the onboard computer in the loop to actually react to the actual systems. And also the simulation of the I/O board and the data and power lines are implemented within the system. And even the payload modules are as dummy models within the system, so you can control the system somehow and see the behavior. There's an additional one where we have our I/O board also in hardware in the system. This system simulation is used to verify the onboard software, most importantly, but also to test flight procedures. So you not only want to be sure that your onboard software works, you can also use your already working satellite as a training for your team, for your operations team, to control your satellite. And you can use it also for the analysis of contingencies during operations. Yeah, we see here the setup. This is the onboard computer engineering model and the simulator. All in here, we have the mission control prototype here and the software development to do some debugging and have some real-time inside views of what's going on with the onboard software for debugging purposes. And this hybrid test bench with the model-based simulation of flying laptop is very unique at this point and enabled a lot of possibilities for testing, especially for the environmental tests. However, you are prone to the accuracy of your models. So you really you really need to make sure that all your models are really close to reality to have a realistic outcome and realistic results of your system simulation with this hardware in the loop hybrid test bench. For the qualification of the main structure and the thermal control system, the TCS, a structure thermal model has been used for flying laptop. Yeah, you can see flying laptop here from the side, and this is the actual satellite. So you see there's multi-layer isolation, there are cables going through different components, structure from aluminum or some honeycomb structures. So it's really complicated to test all at once. So that's why we started with the structure thermal model to prove the structure and to test the TCS at a very early project stage. And the design is that we have component dummies with the same mass, shape, and surface as the later on unit. And those are equipped with heaters and temperature sensors. So we can heat the unit from the inside so it behaves like the later on unit. And the sensors are used to determine the temperature in terms of balancing with other units and other influences. The primary structure of flying laptop was then used with the component dummies as a one unit, it's a PFM. And additional qualification has been done for the middle solar panel, for the cameras, camera baffles, some antennas, deploy mechanism, and multi-layer isolation and battery. So those were additionally qualified aside from the structure thermal model. And the tests that were performed with those units and the STM were the vibration tests and the thermal balance tests. And that was all done in a time frame of around 6 months. Furthermore, at the same time, the FlatSat test was performed. So the FlatSat test is used to check the compatibility of all components under nominal electrical conditions. So you connect all the units you have to the actual engineering model harness of your satellite. But all the units are just on a flat table. So you don't integrate into your system, you just put it on your workbench. You have all the components here, and you connect them with each other and test if they are working and communicating with each other. Yeah, and you can use that for the command and control with the ground equipment. And you start with the engineering model components, and you end with the flight model, model components at the end. And as we said, everything is done before integration, because when you detect any failures, any problems here at this point, you still can access, and you can replace those units or cables or whatsoever you find there. Once it is integrated in the satellite, it's really complicated to do that. And you do the same for the payload and the bus, the satellite bus separately. And it is very important to identify those compatibility problems as early as possible, because then it saves a lot of time compared to a later detection. We actually identified some problems there during the FlatSat tests. For instance, there were pin assignments wrongly done, so we had to change the harness or the connectors. There were some grounding issues where you had issues between the units, and software bugs for the control of the units were early detected already at this stage. Then let's talk about antenna tests. So also the antennas of flying laptop have been tested in different ways. So this is one in the compact test range, the CRT in Oberpfaffenhofen, Germany. So you want to determine the three-dimensional antenna pattern in terms of gain and polarization of your satellite. So you put your satellite into an anechoic chamber on a robotic arm. So this is actually the first time that flying laptop was flying. And you have two mirrors, one mirror here and one mirror there, and a test check up there with a test antenna to communicate via those two mirrors with the satellite. And the compact test range is used to simulate far field conditions, although you're still in the near field. So far field conditions basically mean that all your waves are flat, on a flat surface coming to you, they are not curved anymore. So as you would, those are the conditions the satellite would see when it is in space, and not just in your testing area where it's really close to your test antenna. And we did that to test the TMTC of the satellite under those far field conditions and to determine several exclusion angles that you can see here. So this is the high gain antenna and this is the TMTC antennas. So two antennas, one on this side, one on that side. And you can see one is transmitting to this direction, one is transmitting to that direction, in the dark colors and the red colors, but in the zone between those antennas, you see some spikes and some really low signal levels there, and this was the reason this test was performed, to determine those ripples in between the two antennas. You can also see the high gain antenna that there is only gain into the main lobe direction, but not to the backside, which was expected for a high gain antenna. Then we have the EMC tests. So the EMC tests are there to simulate and to show that you can maintain your own function despite the influence of external and internal electromagnetic fields. So you apply some electromagnetic fields from the outside and you test that the satellite continues working without being influenced by those external signals. Why do you do that? Well, you might be prone to any EMCs during your launch or by other satellites once you're in orbit. They might interfere with your satellite and you want to make sure that this is not the case. And you also want the proof of performance to not interfere with the launcher or the prime satellite in terms of the ride-share mission. So it also is vice versa, that you are not introducing any electromagnetic fields that might interfere with other players in your surrounding. Generally, there are 4 cases that we tested during the EMC. So you check for galvanic coupling, so that you check the conductive path. So is there any EMCs that go through the cables inside of the satellite? You have the capacitive coupling with electromagnetic fields. You have the inductive coupling with magnetic fields and the radiative coupling via electromagnetic radiation. So those are the 4 test scenarios you go through within this EMC test chamber. And all the tests were successfully performed with Airbus in Friedrichshafen, Germany. Then the vibration tests, so the physical tests of the main structure were performed in Bremen, Germany, with the goal to prove the resistance against vibrations during the launch and to determine the eigenfrequencies to avoid dynamic coupling between the satellite and the rocket. Yeah, you don't want to have the satellite swinging or being coupled with the frequency and the eigenfrequency of the rocket, so it might just damage the whole satellite because you hit a resonancy there. And also you want to prove that everything was correctly assembled. So by shaking it, well, if you did a few screws not into place, you're probably going to realize that during the shake, the vibration test and the shaking of your satellite, everything falls out of it. And yeah, those tests were performed for the resonance search, for sinus and random tests for each axis of the satellite. And to do that, there were 12 acceleration sensors installed within the satellite at all the critical positions, and then you can have this, this graph you can just get there with the acceptance load. So this is the test level here, the green one, and the reply level, and those are the acceptance levels for different launches. Yeah, so this is for the PSLV, and this is a test level for the red one is for Soyuz. So this was tested with the Soyuz, and this is the PSLV. Sorry, this is PSLV. This is Soyuz, and the other one is the Soyuz qualification level. Okay, so they have difference for the qualification. This is the qualification you need to show, but these are the actual ones there. Then in terms of environmental testing, more of flying laptop, the thermal balance and thermal vacuum tests were performed, which you already know. The goal is to prove that the satellite can be operated in a space environment within the extreme temperatures and the vacuum. And we simulated the operation cycles during eclipse and sun phase, but also during different operation modes. Yeah? You might have an idle mode where the satellite is not doing much, so it's not generating so much internal heat. Whereas if you go for the payload operation, there might be more excess heat at different points, and you want to verify that your thermal control system is able to cope with those influences. And of course, one very important goal was to verify the thermal model through reference measurements. So since we have a thermal model already done in some software, you want to verify that your software model is in sync with the reality, and that's why you use this test also. So here we put the satellite into the vacuum chamber. So we have the satellite here, and we have the thermal solar panels in front, so thermal simulators to simulate heat coming in towards the heat or cold coming towards the satellite and the solar panels. Same goes for the star trackers, and everything is in a shroud within the test facilities. Yeah, and you can see the flying laptop was lifted into this thermal vacuum chamber and this simulator. 2 tests were performed, one with undeployed and one with deployed solar panels, because those are the different conditions you had to test for. And then you would go through the thermal balance and the thermal vacuum test here. Then there were communication tests that were performed. So the communication tests with Weilheim Germany were performed to verify the communication subsystem after integration. So you want to assure compatibility with the ground station network later on. So you actually take the satellite, in our case the satellite, for bigger satellites you only use the communication subsystem with some external components to operate it there. You go to the ground station, we put it into the test chamber, and it will be directly connected to the antenna. And the antenna has a shortcut and straight feeds the signal back into the system as coming from space. And then it goes all the way through the ground station, through the modems, the software, and you need to make sure that all the systems can process the data correctly. And once you have shown that all the setup was done correctly and the configuration is done with the ground station and the equipment, you can use, you know that your satellite is compatible with all the ground stations that have the same components and the same equipment, with the same configuration. And that was also the end-to-end test with the satellite being in Weilheim. So here's the satellite wrapped up, being connected via the ground station antenna in the loop. But the satellite was not controlled from this room. It was actually controlled via Stuttgart, which is also later on the case. You connect to a ground station somewhere, and then you communicate with your satellite, and this was tested with the satellite being physically located far away from the operation center. Furthermore, there were more operation tests performed, especially the 1 week in the live test. That was very close to the actual launch of the satellite, where the operation team came all together in shifts and controlled the simulated satellite for 1 week under realistic conditions. So at that point, our ground station, our ground control center connected to our hardware in the loop test bench with the satellite completely simulated, and the simulation was kept running for minimum 1 week. And it was tested that when you operate the satellite as you would operate the later satellite, that no contingencies are there, and if there are some, so we introduced some test cases so in order to train the operations team. And the second operation test was the RFCOM test in Stuttgart, where the actual satellite was still located in the clean room and connected via a coax cable to a test antenna, and then was communicating via free space to our actual ground station antenna in a different building with all equipment there. And via Ethernet, those signals were being fed back to the control room. So we also had a verification that the satellite was working with our own ground station under realistic conditions. And once this was all done, well, it was time to ship the satellite over to the launch site. And the whole testing doesn't stop with, the satellite is being built now and you are on component level. There are many more tests closer to the launch depending on your satellite system. And one example here is the separation test. So this is for the Soyuz, where we use our Mars dummy, which had the same shape and the same mass as flying laptop, and which is connected via the launch adapter, which is later on the same used with the rocket. And the separation was tested there, that everything works well, and we could acquire some measurement data. You can see there that the satellite is connected to the launch adapter and is being pulled away from the counter, away from the satellite on Earth. And then with explosive loads, some bolts are blown away, and then with a spring mechanism, it's being pushed away into space. And we use this to get the peak data for our satellite and also to determine the velocity that the satellite is going away from the launch adapter. Lastly, there were some fit checks to be done, mechanical and electrical fit checks. So there were some tests performed if the satellite would actually fit into the launcher bay for a rideshare mission. So the clearances are all there to the other satellites. This is the mechanical fit check, but also the electrical fit check. You can see here. In our case, we had to charge the satellite even once it was already installed inside of the Soyuz rocket. So in the morning of the day of launch, we connected lastly our battery chargers to our satellite to charge the batteries before putting it into space. And there's a bunker right below the launch tower of the Soyuz where we connected our charger and tested the connection all the way through the rocket umbilical cable, as can be seen here, on top of the launch tower here where it would connect to the satellite and all the cabling is correct. And of course, some final checkout was performed in Baikonur, where you have the final tests, especially software tests, and the last verification before you send it up in space. That's it to satellite testing. Thank you very much for your attention.